Yeah, good day. So today we just want to chat a bit about um, trading, concurrency, and multi-processing. For many of us who are into software engineering, we realize that more often than not, when we want to optimize APIs, we tend to think about how do we optimize for space, optimize for time. So the concept of trading readily comes to mind. Could I use the concept of trading to speed up execution of code line, or could I use concept of multiprocessing to speed up the concept of uh, the execution of the code, how fast the code will run, and things like that. So I just want to walk us through trading. Then we talk about concurrency as a result of trading, and then we look at the difference between trading and multiprocessing. So that's what this video is expected to teach us. So the trading is a kind of, so let's, by way of definition, trading is a lightweight unit of execution inside a single process. So with trading, your program can appear to do multiple things at once. For example, you want to download a file, you want to update a user interface, you want to log status. So all of that you can script in different functions. So like I said here, is a unit of lightweight unit of execution. Trading, they are best for input and output bound work, that is like network call, file read, waiting on an API. So sometimes when a client sends a request from the browser and then it gets to the server, so there's a kind of latency or delay between the communication in those cases. So you want to look at how do you optimize the wait time between the request and the response time? How do you optimize for the execution of the code line? Could there be other processes that could be running while uh, a process is waiting for the other? So that is the concept of input and output here, kind of input and output bound. Thread also may usually not be faster for CPU bound work. We are going to see an example in this video of situations or cases where threading might not be excellent and when they will be quite useful. So we'll be looking at a process is just um, a running program in its own memory. So when we talk about process, we're talking about running of a program in its own memory. So then we talk about the thread, which is a process that shares memory with other threads. So you have a process, you have a number of processes that are sharing memory on a computing device. So we talk about threading. If you have a single process, using a single process is a single threading. When you have multiple processes using the same memory, then you talk about multi-threading. So we're going to see multi-threading now. Then concurrency is a situation that arises as a result of multi-threading. That is, there's an overlap in the usage of the memory of the computing device. So we are going to see parallelism and how that is different from data lock, which is the compiler. In a Python, you have an interpreter, and that is the transfer or the conversion of the high-level programming language to the machine language. So we are going to see the C Python, which is the interpreter. There's a way the C Python naturally locks the variables within a function, except when it is computationally intensive, and that's when there's an overwrite. We are going to see an example in this case. So sometimes for processes that are not quite fast, you might not see the effects of parallelism on the function execution because of the GIL, which is the global interpreter lock that CPython will automatically enforce on a variable. But when the computation becomes intensive and it's long, then you see that the CPython interpreter will have difficulty in enforcing the global interpreter lock on the variables. So we are going to see some examples here. So the examples will be about trading, and we are going to see cases where trading applies, how trading happens in terms of the time to run the program, and also the overlap and the concurrency. And from there, we are going to see how to enforce data integrity when there's no overwriting. and from there we'll see the multiprocessing, that is running different running program at the same time on different CPU cores using multiple CPU cores. Okay, so let's just look at the code line here. So here is the code, just some Python program, just to show some of us the examples. So we are going to see this code line here. It's a single thread. Let me just show you what it is. So this is the function here, or let me just go there. So this is it here. So we have a class, we just say in a threading, and then we have a method on this class. So we also have this static function. It's a Python class, and I believe many of us who are familiar with Python syntaxes will not struggle to understand this. So this is just a function, and this function is to print out the variable name, sleep for the number of seconds, and then print out the variable name that it is done. So we just want to know when it starts, it sleeps, and then when it ends. So that's what this download sim will be doing. And we are calling this download sim inside this function single thread demo. So you can see we are calling it, we give it a name, file1, file2, file3. So this file1, file2, file3 will be the value of this variable, or the value of this argument name at the 3 instances where we are calling this function. So the default 2 seconds we apply, because we are not passing a different argument to this function here. So we are going to run this program now. Because we are calling this download sim 3 times, it shall be a single thread. And you shall realize that because we shall be waiting 2 seconds for each call, and we are calling it 3 times, so the total number of time should be 2 times 3, which is 6 seconds. Again, let's see. So we have this function here that we are calling. We are initiating the start time here. We are calling this process download sim. We are calling it again here, download sim. We are calling it again here, download sim. And then we now want to print the difference between the start time and the end time. And we are rounding up to 2 significant figures. So when I run this, it's going to execute this code line, then execute this, execute this, execute this. While executing this, it will call this function. So you're going to see file 1 starting, it will sleep, then possibly you say file 1 done, and then file 2 starting, sleep, file 2 done, file 3 starting, sleep, file 3 done. So that's what we expect, because this is a single process using a unit memory, and then because it's going to run procedurally without any concurrency, it's going to take 2 times 3, which is 6 seconds. So we're going to see that. So each task wait 2 seconds. A single thread will take approximately this. Running a program in its own memory. So let's run the program. So to run the program now, I wrote it in form of an argument parser. Let me just clear this. Let me clear this console. So it's going to be Python demo kind of option kind of optional argument there, and then I want to run the first one. So because I stated right here that I'll be running, I give it a variable. The way I run it is just like index. When I pass 1, I'm going to run this single thread demo. So when I pass 2, I'm going to run this, and so on and so forth. So when I pass this now, it's going to run all this. So I'm going to pass it now. So you see file 1 starting, file 1 done, file 2 starting, file 2 done, file 3 starting, file 3 done. And look at it, it took 6 seconds. It took 6 seconds here, because we have single process in its own memory being called 3 times, and for each time it's waiting for 2 seconds. So the total time will be 6 seconds, because to actually compute each function is far less than a nanoseconds. So the execution of the printing is highly insignificant, but the waiting is dominant, and that's why we say 2 times 3 seconds. So then let's proceed to the to the second example, which is multi-thread. So this is the multi-thread here. So in this case now, this is how you write, based on older versions of Python, you write the threading like this. Later on in this video, I will show you the modern, most updated Python syntaxes to executing thread. So you say in a multi-thread, you want to still execute this function, download scene. And you want a group of functions to run concurrently to share the same memory. That is, to run inside the process and share memory with other threads. So because we are saying to range from 1 to 4, we are going to trigger 3 processes now. And these 3 processes will run within a single memory. It will be a shared memory. Now, because of the concurrency, there will be an overlap in time. Because if you look at this download scene, we want this function, while the code line under this function being executed, we want it to wait for like 2 seconds. And when you run the first process in that thread, there's a trigger to wait for 2 seconds. When you run the second one, there's a trigger to wait for 2 seconds. So when you run the first one while waiting for 2 seconds, the second one can continue to work. And then when the second one is waiting for 2 seconds, the third one can start. So while the first one completes, the third one could start. So you can see, while one process is waiting, other processes could start and could end. And then the other one can take it up. So because of that concurrency in the process, it makes the execution time of the entire thread to be faster. Because to run the 3 processes will be faster because it was done concurrently. So it's a multi-thread, 3 processes, multi-thread, sharing memory, a single one, concurrently. And concurrently, that's the concurrency, which is an overlap. So when you run this now, we expect, since we are going to run 3 processes, we expect the execution time of this to be less than 6 seconds. Because this was a single thread, 3 processes, 3 function, single thread, took 6 seconds. Multiprocessing, 3 process, 3 function, multi-thread, instead of a single thread. In this case, we expect the time to be less. And that is what will lead to the optimization of the API or optimization of whatever process that was built using this threading technique. So when we run this now, we expect the runtime. That is, by the time we print the thread time, we expect this time difference to be less than 6 seconds. So when I run it now, we are going to see that multi-thread demo. So I'm going to pass second argument and we expect to run that. So I'm going to just run that 2, and then you see file 1 starting, file 2 starting, file 3 starting, and then you see file 2 done. You can see that file 2 was done before file 1 was done. File 3 started the thought to start, but it was the second to finish. So that was the overlap. You can see that it was not sequential. It was not, procedural. And you can see the thread time actually took 2 seconds instead of the previous 6 seconds that we had for the single thread. In the case of a multi-thread, we have 2 seconds. This is like saving, this is just like 1/3 of this entire thing. So you saved more than 60%. Yeah, this is just, yes, look at it. It's so quite fast. So this is like 3, this is like delayed by a factor of 3, and this is just like save a huge time. So that's about single threading and multi-threading and the concurrency that takes place within multi-threading. So we shall also be looking at some situations when multi-threading might not be the best option to optimize your code, and we are going to see that. Like I said in the introduction, you use multi-threading when there's a kind of input and output process. Because most input and output process, there will be a kind of latency or a delay. There will be some wait. Maybe when you send a response, a request to a server, before there will be a response, there will be some delay. So when you have multiple requests from different users to the same server and expecting different responses, there will be collection of delays and latency. So situations like that, you can optimize the response of the API using threading. There are other techniques, but today we are just focusing on threading. So now let's look at the CPU single demo. So in this case, we're looking at in a situation where multi-thread does not help. Like I said, it will not help because of the global interpreter lock, which is the interpreter within Python, a kind of C Python. That's the conversion of the high-level language to the machine learning language as in bytes. So when you run a single process like this, which is CPU work, so here we are just doing a kind of we are iterating through this line 200,000 times, and then we want to print the final value of x and we return it here. So that's what we are doing in the CPU work. We just want to look at when you do something like this computationally intensive iteration, would multi-threading or single threading, would they improve on the response time or not? So that's the investigation we want to see. In this, you can see we are not doing any latency here. There's no wait here. We just want to run an iteration that will be lengthy, reasonably lengthy. And let's see whether when we use single thread and multi-thread, is there a difference in the execution time of that function? Just like we had in the previous example. So let's see. You can see the difference here is that in here, we are running an iteration of 200 times, but here it was just a printing we were doing, just print, we wait and then print, which is a less computationally intensive function compared to CPU work here. This is a CPU work, 200,000 iteration, so we are going to see that here. So in this case, we are going to do a single thread on a CPU work, and here we shall be looking at the multi-thread on a CPU work here. It's still the same. Here we are calling two processes in a single thread, and here we are calling two processes in a multi-thread code line execution flow. So I'm going to run the two. We're going to see the difference now. So we are going to pass the third argument to this, the third index, and then we are going to pass the fourth. So when we say this, I will say 3. It's going to run that CPU single. So you see that 200 times. You can see it took 1.21 seconds for the single thread. You can see the iteration. This is close to 200. Yeah, if you look at this, approximately 200,000, because in Python it starts from 0 and it ends with whatever the index is minus 1. So the 200,000 minus 1 will be all of these. And you can see, so it does the iteration and then return it, because we call two processes. That's why we call this. So that's why you have value of x here, value of x 2 times. And then single thread. So when these two finish running, then it executes this line and then it returns this processing time. So then we are going to run this now. So instead of single thread here, we are going to do multi-threading here. So you can see here we are using this threading module. We are using this method on it, a threading module, this class on it, and then we are now going to run this method join on it. We start it and then we join it. So again, here we instantiate the class. We start the class using we start the class using the start method, and then we gather them in a list, and then we iterate through the list and then join each of the instances. So by the time you join them, I haven't started them, joining them, we schedule them to execute concurrently. So that's what is going on here. So when you run this CPU thread demo, we run it here now. We want to compare the time. Will this lead to a shorter time code line execution or otherwise, or the same? Let's see. So when we run this now, say 4, so you see it led to, in my view, approximately the same time. There's no significant reduction here. Let's run it again. So you can see it's fairly greater than 1 seconds. If you run the number 3 again, anything above 1 second, you can see it was previously 1.21, is now 1.16. It was previously 1.27, it's now 1.0, this one 1.37, 1.08. It's just approximately 1 second, so to say. So there's no difference when you are doing a computationally intensive code line execution, computationally intensive, which is not input or output, no latency. Whether you use threading, single threading, or multi-threading, you don't expect any shorter processing time. So we can see that in this case, when the CPU work is intensive, threading does not lead to any significant code line running. It doesn't lead to a faster API. It doesn't lead to, it's not quite useful. And we are going to see example of processes like maybe when you are doing some machine learning model training, or when you are, let's just review machine learning model training, kind of CPU demanding projects. They are not, threading will not be useful in those cases. So let's just see the third example here. So let's see this. So we are talking about a shared without lock, shared data race condition. So when we talk about single thread, a procedural code line execution, then when we talk about concurrency, that is multi-threading, there's a concurrency of the execution of the processes, and that's what leads to a shorter time. However, in the process of concurrency of the execution of the processes, there might be some race condition in the overwriting of the variables, and that is what a developer should be aware of. When you are scripting out your code, do you mind if there's a race condition that will introduce a bug, or you think race condition is acceptable and is factored into your development? Because there's a possibility for race condition if the variable is not expected to be globally immutable, or you want it to be immutable such that you can easily overwrite on it. So that is it. So when we talk about, when I mean by immutability is that when the variable with respect to a particular process, do you want another process not to be able to overwrite on it? Two processes, you use the same variable, you are updating them in the two processes. Do you want process 2 to be able to overwrite the memory, the count of the assignment with respect to process 1? If you use, for example, use the same count as a variable in process 1, which is being updated in process 1, and process 2 also uses count and is updating it. Do you want the update of process 1 to be useful or to be accurate with respect to process 2, or you want a process 2 to have its own separate memory counter? So those are the kind of race condition we're talking about. So let's just look at an example here. So we have this just kind of class here. So we have a counter here, which is a class variable here. So this is a method here, is a class method. We are setting up a counter here. So it's just an iteration through 100,000 loop. And then we are updating the initialized counter at each iteration by 1. So we just want to iterate 300 times, and of course we want this counter to increase by 1 in every loop. So at the end of the 100,000 loop, you expect that to be 100,000 to be the value of the counter. Now, so this is for the increment. Now, if you run this increment multiple, if you run it in a single thread, or if you run it in a multi-thread, this counter will not behave the same way, because two processes or multiple processes might have access to this variable and they might be overwriting on it concurrently. So when we run two processes, for example, on this increment function, we will ideally expect the value of the counter to be, for example, if this is 100,000, each process should be 100,000, the other one should be 100,000. You expect it to be 200,000 at the end of two processes. But when you run it in a thread, it will not be 100,000. So that's the race condition, because there will be some concurrency on that variable, and there will be some, overwriting of previous references of the value of counter. So that's the example we want to see. I want to see the effect of the race condition. So we are going to run two functions here. So this is the shared without lock. So this is the one that have race condition. We're going to run it now. So we've got a process here, and then we have another process here. So we are starting these two, and then we are joining them. This is another way you can write multi-threading. So we're going to run this now, and we want to see the value of the counter after running these two processes in a multi-thread. So this, let's see the argument we are going to pass to this. So we're going to pass 5, and then we are going to run this. So let's see. So when we run 5, you see the value is 100,000. Well, let's run it again. 5 again is 100,000. Though we ran 2, but because of the overlap, the value remained 100,000. Now, when we run, so we run increment here. So when we run this now, increment with lock, the only difference between this increment and increment with lock is that on this line we are putting here a wrapper that we want this variable under this wrapper to preserve the variable of counter. If a processes keep it to be 0, with respect to another process, it might not be a 0. It should maintain its own index and its own iteration increases. So there will not be an overlap. There will not be a race condition. When you are locking the variable with respect to each process within a multi-process system or multi-process code line execution. So that's what we want to do here. So let's see. So we are calling this in this function. So the one we ran now was shared without lock, and now we are going to run shared with lock. So to run the shared with lock, let's see the arguments. We are going to pass argument 6 now. So let's look at it properly. Shared with lock. So we're going to run these two, and we want to see the value of the counter again. So let's pass number 6. So you can see it's 200,000. The two, we are now running multi-process of two processes in a multi-thread system. Multi-thread I meant. And then you can see that because of the lock, the first iteration was 0 to 100,000. The second was 1 to 100,000. So because of the lock that we kept in here, there was no race condition on this variable. So developers need to factor this when they are scripting. When you are using multi-threading, where there is a kind of concurrency, there might be possibility of race condition. So this can happen in a database, it can happen in your API call, it can happen in your user interface. These are, that's the front-end stack or database administrator development and things like that. So these are the instances where you might have issues like this, where you might use threading to improve on the runtime of your code, and then there might be race condition issues that you need to address so that you don't have bugs or problem. So now, so that was the issue of race condition with regards to concurrency. Now, but let's look at this thread pool demo 1. So in this thread pool demo 1 now, we just want to show these previous approaches of multi-threading in current developments based on the latest version of Python 3.8 plus. You don't use this, you don't write multi-threading using this function. You use something like this. So you write it like this. So you can see you instantiate this class, assign it to this variable, and then you use this method on this. So here you have a list comprehension, and then you are setting up you are instantiating your processes here. So in this case, we want to have 5 processes. We are saying for I in range is 0 to 4, we are creating these processes. So this is a process here, self-task. Self-task, let's look at it, which is this. So we just want to sleep for 1 second and then return the string done. Let's say done 1, done 2, done 3, done 4, and things like that. So that is what task will do. So let's look at it again. Self-task. So this is just, like I said, more like a kind of wrapper, just like some of us, there's a way you use some of these, just to ensure that every code under this block will be within a single, in terms of atomicity, there will not be overwriting there will not be a kind of concurrent usage of the memory of the CPU. So when you instantiate a wrapper like this, so that's what we are trying to do here. So while we instantiate this, we want to execute this code line under this block. So we have an executor. So this will create the processes and then to put them in a list. So we have a list of 5 processes, and they will be assigned to the variable features. So on this line, we are now iterating through this list of processes, and then we are obtaining their results. So you can see a different method of executing multi-threading. So instead of creating a process and then you run the stats on it and then you run the join on it to trigger its execution, here you just use some of this method as completed, and this threading class, we are importing them from concurrent feature. So these are modules in Python, they are built in Python. So we are importing this class, we are also importing this method right here. So let's see, so we're going to go here. So this is just a kind of updated method of multi-threading writing, and we are going to see how this will work out. So we're going to run 5 processes. Now each time is going to wait 1 second. Ideally, if it were a single thread, it should take a minimum of 5 seconds to run this. But by the time we run it now, you see that it's going to be faster. Also, we are going to see the count. So the count, so let's just, I think in this count, because we are running this task, we are not actually updating count here. We just want to check the time. We are not updating the count. So I expect the counts to still be the same. So let's just run it. So this is going to be the code line 7. So we're going to pass 7 now, and we are going to see that. So you see, so like I said, the count is going to be 0. So this is, you can see now, 1, 2, 0, 4, 5. So it was not, if it were a single thread, the execution of the process would have been would have been procedural and sequential. It would have been 0, 1, 2, 3, 4. But because it was a multi-threading, there was a kind of concurrency of the execution of the code line. So you can see the first process that was executed was 1, then 2, then 0, then 4, then 3. It's a bit random. So that is the concurrency. And you can see the time, it took 2 seconds. If it was single thread, it would take a minimum of 5 seconds. Because for each process, there is a sleep of 1 second. But because of the concurrency, while the memory was waiting based on the first process, it could simultaneously be processing some other processes, such that within the multi-thread system of a shared memory, you can have the entire processes completed within a shorter time. So that's the idea. So let's also see another interesting example here, which is the thread pool number 2. The thread pool number 2. So here, what we showed was just, updated version of writing multi-threading, and we could see the concurrency there. When we talk about concurrency, we also talk about race condition, and I've showed you how you can avoid race condition. Now let's see this example here. Now here we are running this task as a process. So here we shall be running increment as a process. So the increment, so you can see that, let me just say something about here, worker. We are using 3 worker here. So this is the benefit of using the latest module within the Python programming syntaxes to develop your multi-process code, because here you can specify the maximum number of worker that will be used in that multi-threading of running your program. So if you put 3 here and you put 5 here, you are going to have many workers, which are just computing machine, being able to execute your multi-threading system. So you use this array to specify the number of processes you want to run, and within a multi-threading system, you can now assign the number of workers that will take care of that. So it's just a kind of memory shared across the worker that will be supporting the multi-threading system you have. So let's look at the thread pool 2. In this case, like I said, we are looking at this process, which is increment. And increment is, let's see, this increment is a function, and what is it doing? It's just incrementing here. That is, we are iterating through a loop 100 times, and there's no lock of the global variable of the variable counter, which is a class variable here. And because there's no lock like we have here, there's a possibility of race condition because of concurrency. Okay, so when we run this thread pool number 2, we want to see the output result of counter after running 2 processes, because we are saying from I is equals to range 2, so it will be 0, 1. 2 processes, just like we did in this class, in this thread pool demo 1, we are now doing thread pool demo 2. 2 processes, we ran 2, okay, here it was 5 processes, sorry, but here it was a different computation, so it will be difficult for us to compare these to these in terms of what we want to achieve with these, but we'll compare this with this, thread pool demo 2 with thread pool demo 3. So let's talk about the thread pool demo 2. Thread pool demo 2, like I've explained all here, but let's just look at, here we are focusing on the counter, which is a class variable, which can also be a global variable depending on how you write your code. So when we run these 2 processes, what will be the final value of counter? And also, how does that impact on the processing time or the runtime of this code? That's what we want to see now. So we're going to run it. But before we run it, somebody can guess that because this is a multi-threading, that the value of counter will not be 200,000. It will not be 200,000 because, like I've shown you in the previous example, there's a race condition on the counter variable, and this is a multi-threading process, and we expect this time to be less than because each time here we are slipping 0. So yeah, but because at least we trigger a slip here, that will allow for a race condition. If you never put any slip there, it will be difficult for us to test the race condition. I think that was just the reason why this was scripted here. Let's just introduce a kind of slip, although the time is highly insignificant, but then it will allow us to test for the race condition. So that's why we put that there. So we are going to run this now. Let's look at the code again. We're going to start here. We want to start the timer of how long it will take all of this to process. So we start this time here, and then we are doing the final time will be computed here. We'll find the difference. So that will be the thread time, and here is the counter. Now, this line here is going to return the result. Now, that's the difference. Let's look at it. Here, we are not returning any results. But when we did for, when we wrote for task, we are returning this string here. So in the modern syntaxes of scripting out multi-threading in Python, you use future result to return the value returned by the function here. So that was why we had done 1, done 2, done 3, done 4. If you never put results here, we won't be able to print out or obtain the return value by this process. So the same thing here, although this process does not return any value, because we stated this here, we should expect none to be returned at each of the two processes we are running here. So you are going to see none twice here because this is not returning anything. All we are doing here is just to we are counting and we are updating the counter. But here we are returning. So we should expect that in this process 2 here. So we want to check out for this. We expect this to be none. We want to check out for that, which we expect to be less than 200,000. And this, we want to see how fast that will be. So to run this now, let's check that. So it will be 8. So let's just clear here. So I'm going to say 8 here now. So you can see it's none 2 times, none twice, because of 2 processes. They are not returning any result. And you can see the self counter, because it was a multi-threading system, and because of that there was concurrency, and the concurrency led to the effect of race condition. So this self counter, like we have here, the value was not preserved in each process, so there was an overwriting, and that's why the final value that was returned because of the race condition was still 100,000, but the 2 processes actually went through the loop more than 200,000. Yeah. So we are going to do a third example now, which is just an extension of this, but the difference is that instead of calling self increment, we shall be calling self increment with lock. So that's the difference between these two. It's still the same 2 processes. It's still the same 3 worker in terms of the CPU available, where the memory will be shared over. And then we're also using this to print out the results, just like we did here. So the only difference is just this. That is, we are locking the variable here. We want to avoid the issue of race condition. Here there was race condition, there's no race condition here. So we are saying under this block, keep the value of the counter in each process separate. So if it is 1 in process 1, with respect to process 2, it is already 1. So process 2 should continue the increase from where process 1 left off. And process 1 too should continue the increase from where process 2 left off. So that is what the lock will do. So because of that, we are going to see the output. It will be different from the previous one we just observed now. So this is thread pool demo 3. We just ran thread pool demo 2. For thread pool demo 3, let's look at the code again. We are starting here, and here too we are going to process the read minus the final time minus the initial time, which will be the thread pool time. And here we are going to compute this also. So we expect this to be different from the previous one. This should be the same because this also is not returning any value. There's no return statement here. And because of that, sorry, let me just go back there. Let's just go back there. Yeah, no, let's go back, step back a bit. Yeah, here. So we are in line 218. So thread pool demo 3. So here, we are, just like we did in the previous one, we are instantiating the processes. So those two processes, we'll put them in a list, and then this will allow us to trigger them and start them for each of them, and this will allow us to collect the results, and then we can compute the time. So let's run this now. Let's, just the arguments we're going to use. This will be argument 9. So instead of 8, we're going to run 9 now. So you can see it returned 200,000. The previous one was 100,000, and this is now 200,000. So we ran it now with lock, which was the difference. There was no race condition, though there was concurrency, but there was no race condition. So because of that, the counter kept the total time the two processes iterated through the loop, which was 100,000 times 2, because it was 2 processes. So we have 200,000 as the final value of the variable count. In terms of the thread pool processing time, well, to some extent, I think it's still the same concurrency and multiprocessing. So this time is almost the same. We can't say this is faster by this because it's just the same multi-threading system. So the only issue we addressed here was just the race condition. Here there was race condition, here there was no race condition. But in terms of the execution time, this time is almost the same. It's still less than 1 second, 0.15. And we went 200 times. Yeah. So now we're going to see parallelism. All the while we've been talking about a single threading, multi-threading within the threading concept. So yeah, let's talk about parallelism. So which is the next concept. So like I gave in the introduction, when we talk about parallelism, so we are talking about the tasks that run at the same time using multiple CPU cores. So within your computing system, there's a way you could use relevant Python module to trigger different CPUs that will be processing a collection of processes at the same time, depending on how you script out your code. So, so that's what we are going to see now. In the case of concurrency, there was a kind of overlap in time. But in the case of parallelism, we are going to see how that can also improve the processes. But when we talk about parallelism, there's no problem of concurrency, of the same processes using the same shared memory, because you have them in multiple CPU cores. And also there's no race condition of a single variable being used in different processes. But in this case now, we now have multiple CPU cores, that is multiple memory, not a single memory like we have in a multi-threading system. So let's look at some examples here and let's see how it works out. I just wrote a class here to talk about the parallelism. So each process has its own Python interpreter. Each process has its own Python interpreter, different core. Each process runs on a different core. So we are going to see that here. So we have this process here. We are calling it increment. It's a function, and we are just iterating through that function 100 times. And we have this here. It's also another function. I call it real increment, because we have a kind of wrapper here where we are saying this variable, lock it with respect to each process in different CPU cores or different multi-processes that are taking place here. So we've got, so when you want to run multi-processing in Python, you use classes like, from this multi-processing module, you use classes like process and value. Process and value. So let's just see. So we just want to say, so here we are going to instantiate this class. We assign it to this variable P1, and then we instantiate this class also. We assign it to this variable P2, and we can start this process. We start this process, and then we can join. That is, we start it, and then we can begin the process, we trigger it, and then we also trigger this to also join. So this is more like the counter. We use this class to initialize this counter, a value of 0, and then we set it here, because this self increment, it takes an argument, which is counter. So when you use the concept of multiprocessing instead of multi-threading, it's important that you use a class called value to set or initialize your variable, or your variable that becomes an argument here. So because increment, like we have shown before, it takes a counter here. So this value will then go here, and then it will be increased at every time by a step of 1. So that is what is going on. So when we run this now, we instantiate this class P1, P2, and then this join into it. And then we want to print out the value of counter after we've run these two. So let's see what it will be. We're going to run it here, and then we're going to run it when it locks. When it does not, we're going to see what it will look like here with race condition. So this is with race condition, sorry. That although you have a multiprocessing system where there's no concurrency within the same memory, but because they are distributed over different CPUs, the variable is also still being utilized within these different processes. So there must still be some race condition, sorry. Yeah, so let's understand that. There's a possibility of race condition in both multi-threading and multiprocessing. So how do you address them is to use the lock. But the difference is that while multi-threading, you have different processes within the same memory of a CPU, but in the multiprocessing, you have different CPUs having different memory, and you have processes that are running, concurrently at the same time. So they are sharing a variable counter across the processes running on the different CPUs. So that's what we are going to run here now. So we're going to run this now, and we are going to see the value of this. So because of race condition here in increments, see that the value of counter will not be equals to 200,000. But because we have addressed race condition here, the value of counter here will be equals to 200,000 in the case of multi-processing. That is, when we have a parallel processes running together. not multi-threading, but multi-processing. So we're going to run that now, and that should be number 9 and number 10. So this is with race condition, with no race condition. So number 10 and number 11 rather. So when I say number 10 now, so you can see that instead of returning 200,000, it returned, we just run this now with race condition. So instead of returning, because this was 2 processes, each of them 100,000, it should have been 100,000 times 2, it should have been 200,000, but this is 100,988 because there was a race condition of the variable across different parallel CPU usage where the variable is being utilized. So when we run the second one here, instead of instantiating this process as increment, we are doing real increment here, where there's a lock of this variable here. Here there's no lock of the variable. Here we iterate through. We are saying while this variable is locked, then do an increase. Here there's no variable lock in different CPUs where the processes are being executed. So we are going to run the second one now. Here, this one, and that should be the argument 11. So we're going to see that. So we expect it to be 200,000. It's going to be 200,000 because we are also still triggering 2 processes in parallel, where a single variable is being used in parallel in 2 CPUs. So we're going to run that now. So you can see that it's 200,000 because there was a lock. This is just an index. I ran this, an index I ran. So this is 200,000. So now we've seen the differences between threading and how the effect of how the phenomenon of concurrency happens, and how the effect of race condition does occur. And also we have seen a case of single thread, multiple thread, and parallel processes where you have different CPUs, multiple CPUs, and processes distributed over those, and same variable could be utilized across those different processes in multiple CPUs. And how do you avoid race condition on that variable counter like we just did here? So thank you for this video. Thank you for following me through. Thank you. Cheers.